Okay, here we go. Video number 3, extending Snell's law. I'm sorry I'm becoming a bit croaky, but talking continually. Having prepared all my notes, I'm doing the videos one after each other, and just getting a little bit croaky. Having done 2 hours worth of videos. Right, extending Snell's law. First thing, a statement that you need to be able to remember, and you need to copy it down. Most things I do on the board, this whiteboard, you need to copy down. So what we're going to do is we're going to take Snell's law, which we've already got, which is n is equal to sine theta 1 over sine theta 2, and we're going to extend that formula so it looks more like actually what the formula is on the data sheet, but we'll come on to that in a bit. So when light moves from one medium to another, its frequency remains constant. That moving on tells us that the velocity and the wavelength can change, but frequency always stays the same. So if I've got a frequency, here's my boundary, I've got air, I've got glass, my beam of light comes in here, we know it bends towards the normal as the norm. We've done all this over and over again. What happens is we already know that the velocity changes. In glass it slows down, so we know that the velocity in glass is only 2 times 10 to the power of 8, whereas it's 3 times 10 to the power of 8. What also happens is the wavelength changes as well, but the frequency remains constant. So if we go back to a very well-known formula, V equals F lambda, and we know what's going on here because we've got velocity over here. Velocities are measured in meters per second. You'll see ms to the -1 in all the test papers and exam papers. I still use meters per second like that. We have got frequency here, which is in hertz, and we've got wavelength over here, wavelength lambda, which is in meters. Now, if we look at this formula in a little bit more detail, frequency stays the same. In other words, if the frequency remains the same, we can work backwards, if you like, from an equal sign. We can work backwards and say that velocity is equal to a constant times lambda, which in itself leads to velocity is proportional to lambda. So what that means is if the velocity increases, then the wavelength increases as well. So how does this pan out, and how does that extend Snell's law? Right, let's have a look at the consequences of that. If we've got velocity is proportional to wavelength, then when you have a graph of velocity and wavelength, then you end up with a straight line. And it so happens that the gradient of that straight line might be useful to us, because we can extend Snell's law to look at velocity and wavelength. So we can measure the velocity at a number of places on this graph, and the corresponding wavelengths on this graph, and velocity divided by the wavelength would actually mean something. Okay, so what we're going to do is look at this. Is we're going to say that the refractive index is equal to V1 divided by V2. So whatever the velocity is outside, perhaps in air, outside the medium, compare it to the velocity inside. That would also be the refractive index. Now we know that already because we did that in the very first lesson. So we've got, as an example, we had n, let's just do the formula again, V1 over V2, and 3 times 10 to the power of 8 in air, and 2 times 10 to the power of 8 in glass, and that is equal to 1.5. So there's a use of that formula there that we've seen. Okay, we also get further formula, extending Snell's law even more. We get the formula n is equal to lambda 1 over lambda 2. And if you look at this graph of v against lambda, you could actually work out the frequency, because the gradient of that graph would be the frequency if you take a value of v and lambda, and at that value of v and lambda, v gets bigger, lambda gets bigger, but it's always the same number because it's a straight line. The gradient is actually the frequency of the light, which remains constant. Okay, so we did some of these earlier, so I've not set that out nicely for you because we did this in video number 1, but we haven't looked at this yet. So in the data sheet, you get values of velocities in various materials, 3 times 10 to the power of 8, 2 times 10 to the power of 8. Divide one by the other, you get the refractive index, which is also in the data sheet. We can use that information here, the refractive index, to work out the variation in wavelength. So this here is a high velocity. This is a lower velocity, 3 being a higher number than 2. So what we would have here is that this would be a higher or bigger wavelength, and this would be a shorter wavelength. So typically we could just pick out some numbers, and we'll do some sums in a minute. But if we know that the refractive index is 1.5, if I knew that the wavelength in the air was 600 nanometers, then I'd know, I'd be able to work out what the wavelength is in glass, say. And if I know that's 1.5 and I know that's 600, then this must be 400, because 600 divided by 400 is 1.5. So I can use these formulae to find out missing values. If you know 2 of them, you can always work out the rest. Now we've also got Snell's law, and Snell's law that we did in video number 2 is sine theta 1 over sine theta 2. That's Snell's law on its own, but you'll see that each of these 3 formulae each involves n, so we can get, well, like 1 mega formula. N equals sine theta 1 over sine theta 2. That's equal to v1 over v2, and that is equal to lambda 1 over lambda 2. And we've got 1 mega formula, and that's actually the formula that's on the relationship sheet. You don't see the 3 separate formulae. You see them all combined in this like mega formula. Number 1, anything with 1 in it, theta 1, velocity 1, Wavelength 1, anything with a 1 in it is in air, and anything with a 2 in it, theta 2, velocity 2, lambda 2, there's velocity 2, is in the medium. And there you go. And we're going to have a look at some examples of what to do. And we're going to look at we're going to look at these because we saw that in video 1, but we haven't really done any calculations. I just gave you an idea. 600 divided by 400 is 1.5. Excuse me a minute. You'll just have to do some writing. I've got somebody at the door. Yes, that's me. Thank you very much. Cheers. Bye now. Amazon calling. Nice parcel. I'll open it later. Right. So let's move on. Example time. Example time. And remember that N, you don't need to write this bit again. You've just got it. Well, I haven't. I've rubbed it out. There you go. There's your formula. Let's have a look. Just having a look at my notes because I've got all this worked out already. Same sort of thing as before. Air. You'll be used to this by now. Glass. No, do a water one. Beam of light here, coming in, 47 degrees here. And we know that when it goes from air into water, it slows down, bends towards the normal. So it goes off like that somewhere. And this angle here is theta 2. Okay. This is red light. And you will either be told what the wavelength is or you will have to look it up. But I'm going to tell you that the red light is red light with a wavelength of 660. I did that little example earlier with 400 and 600. So the red light would have been round about 600 nanometers. And 400 is more towards the greeny blue end, the shorter wavelength, 660 nanometers there. So here we go, red light. Okay, and once again, you should notice straight away that this is not theta 2. Theta 2 is the angle between pins left, had its cap left off. Theta 2 is the angle between the ray of light and the normal. So here we go, calculate or find theta 1 and theta 2. Theta 1 is 90 degrees, take away that other angle. So that must mean it's 43 degrees. Theta 2, we're going to have to use some variation of this formula. So what information do we need? What have we got to find theta 2? This is a repeat of the last question, really. Which bit of the formula we're going to use? We're going to use this bit first. Okay, so we're going to use n equals sine theta 1 over sine theta 2. And that means that we get 1.33 equals sine of 43 degrees divided by the sine of theta 2. We can rewrite that. Remember, 1 mark for copying down the formula, 1 mark for just sticking in the numbers that you know. All right, and then the final mark for doing the calculation and getting the appropriate units here. So there's going to be another couple of steps, because we're going to put the sine theta 2 up there. We're going to put the 1.33 down there. We're going to enter that into our calculator, sine 43 divided by 1.33, and then we're going to do the inverse sine whole thing, which is exactly what we did before, running out of space. So I'll just move straight to the next bit. Sine theta 2 equals sine of 43 degrees over 1.33. And when you do that, you get 0.513. So theta 2 is the inverse sine of 0.513, which is 30.8 degrees. That's just the same really as the question that we did earlier on. Okay, the next thing we can do is we could find the speed of light in water. Now, I know we know this because we've done this before, but we're going to have to go through the calculation. We're going to use the next bit of the formula there. So I'm going to rub out that bit. I'm going to rub out that, but just to give myself more space. And we're going to use this time N is V1 over V2. And we're going to find, I should write that down first, find the speed of light in water. Now, I think it's fair to say that if you were going to get this question in the exam, the speed of light in water would not be in the data sheet. They take it out, and they can, in fact, change the data sheet from one year to the next. They've been known to do that. If you then just pick a number out of your head, oh, yeah, I can remember we did this lots of times with Mr. Ford, and it's 2.26 times 10 to the power of 8. But if they give you a very slightly different refractive index, and you just write down 2.26 times 10 to the power of 8, you've found it, but it's the wrong answer. So you're probably not going to get the information given to you in the table to look up. You're going to have to use the calculation method. So what have we got? We've got N, which is 1.33. Again, write down the formula, 1.33. We know the speed of light is 3 times 10 to the power of 8, the speed of light in air, and we want to find the speed of light in the water. We can then do some cross multiplying, V2 rearranging, 3 times 10 to the power of 8 divided by 1.33, and we'll get our number, which we are expecting to get anyway, 2.26 times 10 to the power of 8 meters per second. We're expecting to get that because we did that right back at the start, but it just shows you again that you need to set out the formula, put in the numbers, rearrange it, get an answer, show some units. Remember, 1 mark there, 1 mark there, nothing for the intermediate step, but 1 mark for the number and the units at the end. And finally, you can probably guess what's going to come up here is we're going to find the wavelength of the light in water. The third part, I can't remember whether it was 1, 2, and 3 or A, B, and C. I'll just do part 3. It doesn't matter. And we're going to use the third part of the formula. We've used the first bit in the first section, part 1. Then that was the last bit, and now we're going to use the third and final bit, which is the last bit of Snell's law extension, which is lambda 1 over lambda 2. Now, this is a ratio. So because it's a ratio, you don't actually need to change the wavelength from 660 nanometers into 660 times 10 to the and then get an answer. You can just do it all in nanometers because it is a ratio. If you've got two wavelengths, you don't have to change the into the correct units, the standard units of meters, and you can just do it, and then you'll get an answer in nanometers popping out at the end. If you want to do the whole thing, you can, and I'll do both because both will give you exactly the same answer. So first of all, I'm going to use 660. Second one, I'm going to use 660 times 10 to the negative 9. And here we go. So we've got method 1, where you can just use 660, and we get, put in the numbers, 1.33 equals 660 over lambda 2. Rewrite lambda 2 is 660 over 1.33, and you will get 496. And if you started with nanometers, you'll end up with nanometers. There's nothing to stop you changing that into its standard form, in which case you'd get 1.33 equals 660 times 10 to the negative 9 divided by lambda 2. Rewrite would give you lambda 2 equals 660 times 10 to the negative 9 divided by 1.33, and that gives you 496 times 10 to the negative 9. It probably wouldn't appear like that on your calculator. It would be 4.96 times 10 to the negative 7, probably, meters. And you could write it down as that, or you could have worked out that when you do that, you get 496 times 10 to the negative 9, because nano is times 10 to the negative 9. You need to remember all these prefixes: milli times 10 to the negative 3, micro times 10 to the negative 6, nano times 10 to the negative 9, and pico times 10 to the negative 7. You need to remember those because they're not going to be written down anywhere for you. And that is just 496 nanometers, or 496 times 10 to the negative 9. It doesn't matter. Right, now, last thing, part 4, is what's the frequency? The frequency where? Well, the frequency is the same, stays the same when it goes from one material to the other. So part 4, or A, B, C, part D, whichever one it is, I can't remember what it is because I keep rubbing it out. Find the frequency of the light. So we can do a calculation. We can do, first of all, we could, if we wanted, we could find the frequency of the light in air. Secondly, we could find the frequency of light in the water. But because of the statement I made right at the start of the lesson, the frequency stays constant, we would get the same answer for both. So it doesn't matter which one we do, whether you find the frequency of the light in air or find the frequency of the light in water, because they're both exactly the same number due to the statement I made. So let's have a look at the air values first. We've got V equals F lambda. And in air, we've got 3 times 10 to the power of 8 equals F times. Now you are going to have to change this into its standard form, which is 660 times 10 to the negative 9. And you can rearrange that. So F is equal to 3 times 10 to the power of 8 divided by 660 times 10 to the power of negative 9. And to save me working it all out, because I've got it written down already in my notes, that is 4.55 times 10 to the power of 14 hertz, if I can read my writing. Now you can do the check, you can do the same thing. It should be the same number if we do this in water. V equals F lambda. Remember, F's going to stay the same. We've got a new V, which we did in the last bit, part 4 or part C, which is 2.26 times 10 to the power of 8. That is equal to 496 times 10 to the negative 9, or 4.96 times 10 to the negative 7. It doesn't make any difference. You'll get the same answer. And I've left out my F. That was a bit of a mistake because I haven't got room. 2.26 times 10 to the power of 8 equals F times whatever I just said. I've forgotten again now. 496 times 10 to the negative 9. And then we can rewrite F is 2.26 times 10 to the power of 8 divided by 496 times 10 to the negative 9. And if you do that, then you get exactly the same answer, hopefully. You might get a very, very slightly different answer because of rounding, and we're only writing down our answer correctly to 3 significant figures, 2 decimal places. You might get something different on your calculator and you've just done a bit of rounding. And sometimes when you do a bit of rounding in the final answer, you don't get quite exactly the same answer as you would do because you've already shown the rounding, but you should get exactly the same answer. And that shows you that the frequency of light stays constant in the material. It doesn't matter whether it's in the air, the glass, whether it goes from air into diamond, air into oil, air into water, air into glass, any other combination you like, water into air, any combination you like, the frequency will always stay the same. And you should watch out for that. The velocity and wavelength change in proportion to each other. Okay. Moving on. Further examples. Just covering all the bases here. Diamond on one side and glycerol. Glycerol's type of oil, as I've mentioned before. Refractive indices 2.42. Refractive index of glycerol 1.47. Again, in the data table, we've got our normal line. We've got our beam of light coming in like that. We've got 65 degrees here. You know what's going on. We're going to get this beam of light. Now, because this is a bigger refractive index than this, the beam of light isn't going to get refracted down here. It's going to get refracted up there. And we've got theta 1 here, and we've got theta 2 is going to be there. And it's green light this time. And green light has a wavelength. There's a number of different wavelengths that you'll find in the data table, but you'll be told which one to use, or they'll give you a specific number. 550 nanometers is the wavelength of the green light. What are we going to do? I'll try and remember it's all letters this time. A, we're going to find theta 1 and theta 2. You should be well clued up now as what to do. Theta 1, because that's not theta 1, that's theta 1. It's 90 degrees minus 65, and that is equal to 25 degrees. Theta 2. Theta 2, not particularly straightforward here because it's 2 different materials, and we're going to have to say, right, it's not the plain simple n is sine theta 1 over sine theta 2. We're going to have to use that sort of double formula where n1 sine theta 1 is equal to n2 sine theta 2. See what I've done there? I've actually got the diamond, all the information from the diamond is on the left. I've just impressed myself here. All the information for glycerol is going to go on the right, and then I can do 2.42, put all the numbers in. Sine theta 1, we've just worked out that that is 25 degrees, so it's sine of 25, and that is equal to n2, 1.47 times sine theta 2. I'm going to rewrite that. I'm going to take the 1.47 down there. I'm going to divide 1.47 into 2.42, 2.42 divided by 1.47 sine 25 equals sine theta 2. And if I do that on my calculator, I know that is, you don't have to write down every single step here in tests and exams, but I'm just showing you what's going on. It's perfectly okay to miss a step if you want. Sine theta 2 times 1.47. No, not times 1.47. Already dealt with the 1.47. What am I talking about? So what have I got? That's, I've just not done that right at all. Not done that right at all. I've missed a step in my calculation. Excuse me a minute. 2.42 divided by 1.47. That's 1.64. Now, 1.64 times the sine of 25 equals 0.695. I'm sorry, I was talking one step ahead of myself. Okay, so I've got the 1.47's gone down there. That's 1.64 times sine 25. I don't know where the I do know where the 1.02 came from. It was that. Just forget me. 2.42 times sine of 25 is 1.02. So all of that side there. Theta 2 is the inverse sine of that lot. 1.64 sine to the minus 1. 1.64 times sine of 25 is 0.696, I think. Which comes out to be 44.1 degrees, I think. Ignore my waffle, but just follow the writing. I was trying to do things a bit too far in advance there. So that works out right, and that's the correct answer. Okay. What was the angle? Whatever it was, doesn't matter. We've done it. And I think that's correct. Of course, somebody will have noticed this that I've done. I've made a couple of mistakes. I ought to go back and re-record the whole lesson, but I'm not going to. Somebody should be shouting at me, and I can't hear you shouting loud enough. That is not theta 2 there. That is not theta 2. That is some angle, but of course this is theta 2. And theta 2 is 44.1. If we were asked to work out that, you'd take 44.1 away. So forget that I drew theta 2 on there, because theta 2, which is the angle measured from the ray of light to the normal, is 44.1. If I wanted that angle, which I had on my original diagram, and I shouldn't have called that theta 2, I could have called that angle X, for instance, then you would just take 44.1 away from 90 degrees. So I'm sorry, I've made a couple of mistakes there. And if you were awake enough, you might well have spotted what was going on. Right, let's move on. I'll get rid of that embarrassing set of mistakes. But you know what to do. We've done this before. That's the first bit. Right. Excuse me while I have a slurp of my coffee. Doing all these videos continuously leaves you with a bit of a druth. Okay. Right, what shall I do next? What shall I do next? I've got a lot of stuff here, but I'm conscious these videos are, you know, they're going to be quite long. Shall I really do the bit with the wavelength? I'm just thinking whether you just have to give me a second whilst I think, and whether I'm going to skip a bit of my notes just to cut this back. I think we might do this. Part B. Find the speed of light. Find the speed of light. Just trying to cover all these options here, which will make the video a bit longer. Calculate the speed of light in each material. Okay. Now we've got diamond and we've got glycerol. You're unlikely to know the speed of light in diamond and glycerol. You're really going to have to calculate them. We know the speed of light in air, 3 times 10 to the power of 8. You might remember 2 times 10 to the power of 8 for glass. You might remember 2.26 times 10 to the power of 8 for water, but we've never worked these out before, so you're going to have to do it. So let's start with diamond. Okay, we have got, we can use our formula N for diamond. You don't have to use this symbology here. You could just put N, it doesn't really matter. But we're going to go back to our big mega formula on the sheet. And quite simply, N is V1 over V2. For diamond, 2.42. And what are we going to do? We're going to have to compare each of these with something that we do know. And we do know the velocity of light in air, but we do not know the velocity of light in diamond. So the velocity, this is going to have to be the velocity of light in air. So we must compare, must compare the velocity in air with the velocity in diamond, and then we can rewrite that. V2 is 3 times 10 to the power of 8 over 2.42, and that comes out to be 1.24 times 10 to the power of 8. Now, diamond is really dense. It's got a high refractive index. It bends light a lot, and it slows light down a lot. And this is the lowest velocity I think we've calculated so far. Let's do the same for glycerol. So I've got glycerol on this side. We can repeat this. Glycerol, the refractive index for glycerol is quite simply V1 over V2 from Snell's law. 1.47. Going to repeat what we've done there. 1.47 is equal to 3 times 10 to the power of 8 over the velocity of light in glycerol. And I'm not going to write down the intermediate step of swapping it around. I'm just going to go straight for the answer. V2 from my notes is 2.04 times 10 to the power of 8 meters per second, of course. Meters. You're shouting at me. You should be shouting out saying, Mr. Farmed, you've missed out your units. That's a mark off. Of course it is. So there you go, the second bit. So they've got different wavelengths, different speeds, different refractive indices, but what do we know about the frequency? We know that frequencies ought to stay the same. we know where we're going on this, but let's work out some wavelengths first. Let's do part C. Let's work out some wavelengths, and then we'll do some frequencies. Now we've just done the velocities and got two different answers. We're going to do the wavelengths and get two different answers. Then we're going to do the frequencies and get the same answer, because we know that the frequency in the materials is always the same. So part C, we're going to find out the wavelengths. And I'm going to try and do these again, one bit on the left, one bit on the right. Okay, so our abbreviated Snell's law, not the whole mega thing, is n is lambda 1 over lambda 2. And for diamond, I've got 2.42 equals. Now I've got to either do this in nanometers or change it into standard form. I don't think it really matters. Let's just do it in standard form just for completeness sake. And I'm going to get an answer in meters. I'm going to change this already, 550 times 10 to the negative 7, or 5.5 times 5.5 times 10 to the negative. No, I'm not doing very well. This is like third lesson in a row here, and I'm cracking up. Okay, 550 times 10 to the negative 9, or 5.5 times 10 to the negative 7, divided by lambda 2. And you're probably sitting there thinking, well, if Mr. Ford can't get it right, what chances have I got? Rearrange that formula. Make lambda 2 the subject of the formula. Lambda 2 is 550 times 10 to the negative 9 divided by 2.42. Don't let any mathematician tell you need to change this to 5.5 times 10 to the negative 7. And you've always got to have a decimal point there. That's just not true in physics. And we're going to get an answer of 227 times 10 to the negative 9. It probably won't be 227 times 10 to the negative 99 on your 9 on your calculator. It will be 2.27 times 10 to the negative 7 meters, but it doesn't really matter there. Okay, if I'm getting confused, I'm pretty sure you're probably away with go and have a cup of coffee. Go and have a cup of coffee. Pause the video. What's the time? Oh, I've been doing this now for nearly 3 hours straight. No wonder I'm cracking up. Right, wavelength in glycerol, exactly the same thing. By now you're probably thinking, do I really need to be writing all this down? Probably not really, but it just goes to show what we're doing. 1.47 equals, what have we got? We've got that 550. It's okay, we can use that. Lambda 1 over lambda 2, 550 times 10 to the negative 9 divided by lambda 2. Rewrite it, lambda 2 equals, just to be daft, 374 nanometers. All right, there's no way you need to do all these different units. Just stick with one and write down what you get. What we're going to do last of all is show that the frequency is the same. We're going to do V equals F lambda here and work out, using our velocities that we got earlier and our two wavelengths that we've got, and we're going to do the two sums and show that the frequency remains the same in every case. So part D is work out the frequency. Frequencies. Okay, we're going to do V equals F lambda in diamond. What do we know? Well, if you go back, we'll have done that 1.24 times 10 to the power of 8 is equal to F times, was it 227, I think? rewrite that, put F the subject of the formula, and we get F is equal to 5.46 times 10 to the power of 14 hertz. If we do that for glycerol, we're going to do exactly the same. V equals F lambda. We're going to get our glycerol speed, which is 2.04 times 10 to the power of 8 is equal to F times whatever it was we got before, 374 times 10 to the power of 14. So rearrange that, and no, that's not right. 374 times. I really am. I should just stop now, really. Times 10 to the power of 9. I'm really just not doing very well here. F, if I divide 2.04 times 3 times 10 to the power of 8 by that number there, I'll just say I'll take that and divide it by that, and I won't try and say them. I can't even say them properly now. And I will get 5.46 times 10 to the power of 14 hertz. And I have shown that the two frequencies are the same. Frequency stays constant in both materials. There you go. Right, I'm going to stop. Because I will just work myself into a complete frenzy here of getting things wrong. And you're sitting there thinking, what is he doing? And the answer is, I don't really know. But we're getting through this. This is like 3 hours straight for me now doing these videos. I don't normally do them straight off like this. Which is why I'm getting a bit lost. Same thing will probably happen to you when you get into your physics exam. I wish you luck, because you'll be sitting there. But this is what you need to do. You need to actually sit there and practice and do stuff, and try not to get really tired towards the end, which is what is happening with me here. So I'm going to stop recording. I'm going to say no more. I'm going to cut my losses, and anything else may come in another video.